Welcome to the second video for how LLMs work. Let's revise on what we completed in the first video. In the first video, we saw what is the long form for LLMs and how they are kinds of brains for GenAI. We saw different types of brains, out of which we took one of them, which is ChatGPT. We saw what does GPT stands for. Then we saw what the GPT is designed for. Next, we saw how do transformers work. Then we saw how Google Translate is the basic primitive type of transformer. We saw how transformers are trained to predict the next word for each sentences until the end of the message or a sensible message. Then we started with a brief intro of the transformer model architecture. Then we came to the step 1, wherein we saw tokenization, the process of giving numbers to the alphabets, then how the process of understanding the words, building the words. Then the step 2, which is vector embedding, where the semantic meaning of words, by the example of how dog understood the words food is related to eat and hunger, which are plotted on a graph. Then we came to the third step, which is positional embedding, which is providing the position to the words in the sentence at the correct place. Let's talk something about the multi-head attention. So multi-head attention is one of the boxes in the transformer model architecture. After we do the so we had taken some text, we had tokenized that text, we had done the vector encoding, the positional vector embedding, then the positional encoding, and then comes the multi-head attention. Before we go ahead to that, let's see one more diagram here. So whatever we are doing till now, it is all a part of GenAI. We are talking about right now is part of GenAI. Eventually, when you will keep on hearing this word GenAI, you will also hear a few more things like few shot learning, one shot learning. There's one more zero shot learning, which zero means you're not giving any example to the model and just asking it to create new content without giving any reference of any example. One shot is giving one example and asking it to create something similar. Few shots it's giving few example and then it learns through the patterns of those example. You might hear the word hallucination, which would mean that it does create something out of its own understanding which does not exist in real world, like some not existing white papers. We have already heard the term agents, wherein agents, the brains which take actions, are called as agent, and we were looking at the transformer architecture of the model GPT, generative pre-trained transformer. Same like GPT, we have something called as BERT. Then whatever we are talking about right now, LLMs, large language models, how they work, and we are talking about the transformer architecture. RNN, recurrent neural network. So what happened is before 2017, so before this all transformer existed, there was something called as recurrent neural network, RNN, And what it did is it used to take sequential inputs, like when we tokenize the word, the cat sat on the mat. It first tokenized all these words and then did the vector embedding, and then sequentially it did the processing on them, on the word. There are two drawbacks of the sequential encoding. One of them is time, it takes a lot of time, and the second is it loses context. Let's take one example. A boy was standing in front of a supermarket and the boy says, I love chips. A CEO of a company says, I love chips. But this time, the CEO of the company was looking at the logo of NVIDIA. Well, both of them have a very different meaning. If we plot of them, these two sentences on a graph, chips and chip, both of them would be somewhere here. But the chips part is the potato chip, and the chip part, which is below, is the GPU chip. There are two concepts here. One of them is self attention, which is also called as single head attention, and the second one is multi head attention. In single head attention, all the vectors talk to each other, and hence they come out with a clear contextual meaning. Multi head attention. Let's understand this concept with one of the sports example. Suppose there is team A and team B. And imagine that you're building an AI model that watches the game. It's a basketball game, and the job of this AI model is that it needs to watch this basketball game and describe what is happening. At this moment, the team A players have passed the ball to team B, and the team B is near the basket. What the model sees is at any moment in the video, there are several players moving objects, a ball, a basket, which is the goal area, and movement patterns. The model must understand who is doing what to whom, similar to how we process language but in visual form. Each attention head focuses on different aspects of the scene. There are four attention heads. Head 1 would track the position of the players. That is, player in team A is on the left and the basket is on the right. Head 2 tracks the ball movement. Ball is moving from team A towards the basket. Head 3 would focus on the interactions. That is, the team A passed the ball to the teammates near the basket. And head 4 watch the background or the context that this action is near the basket area. Each head pays attention to different relationships within the same frame or sequence of frames. When all the heads' outputs are combined, the model gets complete understanding of the play. It can generate a description like the team A passed the ball to the teammates near the basket. If there was only one head, the model might focus just on the ball, missing the context of where or who is involved. So now we have been talking about single head attention and multi head attention, but this all is based on a concept which is used in Transformer, which is QKV. Assume that you are running an SQL query. Uh, you enter the query, and the first step is actually it finds the tables which have those primary keys, set keys, and after that, it finds the value inside that table. So, query key value. Assume, just for comparison, assume it is like how you run a query in SQL. Now, this process attention mechanism, which is used by LLMs, the core idea is to allow the model to dynamically focus on relevant parts of the input sequence when generating or understanding text. So we have a lot of text, but what is the relevance? What is the context? That is something which attention focuses on. And how it is achieved? It is some scaled dot product attention, and inputs are the tokens. So we had the words and later we converted them into tokens, then those vectors came, but these vectors, on top of these vectors which we have for that particular word, we also have three other types of vectors which are query, key, and value. And these are learned projections of the input embedding by a linear transformation matrix. So, what does query talk about? Query talks about what am I looking for, and key talks about what do I have available. Okay, same as SQL query. What am I looking for is your SQL query, like select star from table, and what do I have available? Which all tables do I have available? And value is whatever we, what do I retrieve? Once the matches are found, you pull the full details from the values, which are the values from those matching tokens, and blend them into a context aware representation for your current word. And this lets the model attend to distant or relevant parts of the text without rigid sequential processing. And softmax process is it ensures the weighted sum to be 1. So everything what you add, it should the sum should be in 1 so that it's easy to know for which word for the probability for the next word from this set, for which word the probability is the highest from this set. So if there's a value 0. 0.1, 0.9 and 0.2, so 0.9 is the word which will have the highest probability for being the next word. Query key value is a very long topic with a lot of mathematical equations. In case you want to have a deep understanding on it, you might want to watch this particular YouTube video. Out of all the YouTube videos which I did search and about all the documentation, this is a video which I found has a very good explanation about QKV if you want to do more research on it. We are yet in the encoder part of the transformer model here. And we've just completed the multi-head attention explanation. So in transformer, in the encoder layer, this is a part of the transformer model that helps it understand input data. And there are sub layers in this encoder. Each encoder layer has smaller parts called sub layer. Two parts are self attention layer and the feed forward network layer. Encoder layer. Encoder layer is a part of the transformer model that helps it understand the input data like words in the sentence. And sub layer Each encoder layer has smaller parts. The two main parts are the attention layer and the feed forward network layer. After both of this, like after the attention as well as the feed forward network, a process happens which is called as normalization. And what happens in normalization? Normalization is a process wherein the data adjusts so it's more stable and easier to learn from. Think of it like making sure all values are in the similar range so the model doesn't get confused. Residual connection. So instead of just taking the sublayer in output, the model adds the original input back to it. So the output is sublayer results plus original input. And what does this help with? It helps the model to remember what it learned before and stops the training process from losing information as it goes deeper. This problem also called as vanishing gradient problem. This same process, as we mentioned, normalization process, this happens both after the attention layer as well as the feed forward network layer. So, in just to summarize, each sublayer like attention or FFN, which is feed forward network in the encoder, normalizes the data as the input back to the output. So the model learns better, stays stable, and can be made deeper without problems. Till now, we have only been talking about the encoder part, but this all has also to be given to the decoder. Suppose I'm giving a sentence to the encoder: Hi, how are you? What happens in the encoder? Let's revise. First of all, it will create a vector for each word in numeric form. Vector. Then it'll add the position, and then it'll understand the context with this all. And then finally, this is the input which goes to the decoder. Along with this input at the start, when the decoder does not have any output yet, it'll just give a kind of label, um, just a specific token at the start, like start. Now the decoder takes the encoder's output, the meaning of hi, how are you, and the previously generated word starting with start, then adding I am good, etc. What the decoder does is it looks at the word it has already generated, like I am good. It masks the meaning, it can't see future word, it only predicts one word at a time. Decoder also looks at the encoder's output to focus on parts of the input sequence. For example, to generate I am good, it might focus on how are you from the encoder output. And feed forward network process this combined information and gets ready to make the next word prediction. Now let's see what the decoder does. So in decoder, there is something as self attention and there is something as cross attention and feed forward network. These are the three steps of decoder. So in self attention, it only has the attention on whatever is done in the decoder. So when we have the question from the encoder, hi, how are you? The decoder has to give the answer like, I am good, thank you. So, but these words which are being generated one at a time, it is giving attention to that. So when I say masked, meaning it cannot see the future words. One at a time it will generate. First it will generate I am, then it will generate good, and then it might generate thanks. So it is not, it is masking, means it cannot see the future word. It only predicts one word at a time. Cross attention. Cross attention means between the encoder and decoder attention. Now the decoder looks at the encoder's output, so which we got previously from the encoder, whatever was the output, to focus on the part of the input sentence. For example, to generate I am good, it might focus on how are you. So in encoder, we had the output as how are you. And the encoder and the decoder's output was, first word was I am. And then it might generate the next word good. But this, whatever is generated from the decoder as an output, it also compares it with what we have from the encoder, which was how are you. So it is comparing I'm good with how are you. Feed forward network. This process, this combined information and gets ready to make the next word prediction. Output of a decoder. Finally, the decoder uses the linear layer and the softmax to pick the next word. What happens is, at the start, this is the output of the decoder. At the start, there's nothing as an input, it's empty. And the output will be I am. Then the next step will be I am. This will be the input, and the output will be good. The next step, the input will be this entire thing, I am good, and the output will be the next token, which is thanks. And the next step, which is the last step, it will be an input, I am good, thanks, and that's it as the end of the sentence. So this is just like an overview of what the transformer architecture is, wherein this is the encoder part and this is the decoder part. Uh, there are a lot of things in it, and it's not possible to cover all of these in details, and it might also cause a lot of confusion. So there's one more thing here which is called as the feed forward network, which we did not cover in detail. And this feed forward network comes from, if you remember this diagram where we understood what is like AI, ML. So we were talking about Gen AI that time to understand few terms. So this feed forward is a part of neural networks. And what happens in feed forward network is there is an input layer, an output layer, and a hidden layer. And there are something called as weights, which are shown in these dotted areas. And there is something called as bias. So inside every transformer block, after the attention happens, we apply a small feed-forward network to each token's vector. And there are three parts in it, wherein we expand the dimensions, then we apply the rectified error linear unit and Gaussian error linear unit, which is the activation function. And then again, whatever we had expanded, we reduce the dimensions. So in the first expand dimension, if the token vector size is 512, we expand it back to we expand it to 2048, because expanding allows the network to capture richer, more complex patterns. And the rectified error linear unit turns negative values to zeros, and Gaussian error linear unit smooths the version used in transformer. And this activation is done. It adds non-linearity, which lets the model learn patterns, transformation, and model complex relationships. So attention gives the token information. Activation lets the token transform the information in a meaningful way. And the third linear layer, which is project back, it reduces the dimension. Like 248 dimensions we have, it again reduces it back to 512. And why this is done? So we can add residual connections. And so next layer can process the vector and shape is uniform throughout the network. And why do we do this process of expanding, activating, and shrinking? Because this combination expands information, transforms it non-linearly, and returns it to standard size. And this gives the model more expressiveness, more depth, ability to learn complex language patterns, and more powerful token representation. And this is why the feed-forward network is also called as a processing brain inside each transformer block. So first linear layer makes the vector bigger, more space to learn features. Second is activation. It adds intelligence, non-linear transformation, and second linear layer shrinks back, fits into model pipeline. Feed forward is like giving each word a private thinking session after activation.